if we look at the tuning forks that you guys were playing around with yesterday in the lab, those are a vibrating object. So we have those two forks, and as you whack the tuning fork with your little mallet, they move back and forth, in and out, and it's not perceptible to you. I mean, you can't... they're not perceptible to you. You can't see them moving, but you're able to hear them, and if you put them up close to your face, you may actually be able to feel the air vibrating. Sound waves are not transverse waves, though we simplify them and think about them that way. So remember, just a refresher, that's a transverse wave. So if they're not a transverse wave, what kind of wave are they? Compression or longitudinal wave. So we have areas of rarefaction, areas of expansion. Rarefaction, expansion. I'm doing this horribly. Of actual air particles. Okay. Okay, so as those air molecules move, they create a compression wave. You can do this by clanging a bell. You can do this by striking two boards together. Anything you do like that is going to compress the air around the object and create these outgoing waves. They travel in all directions from their source. And what that means is spherically. Literally, there is a sphere, a bubble of sound traveling out from any vibrating object. And you can really mess with your own head by walking around today thinking about people as they walk down the hall talking, and the sphere of compression waves that is emanating out from them, and picture their heads encased in bubbles of sound moving out as a visible membrane. It's kind of fun. Unless they're blocked or their direction is in some way changed. So, if we have a little bell, here's my little bell with my little clapper, and I ring that little bell. And you know, this is the typical cartoon, it shows that something's moving, and actually is a pretty good representation of sound waves moving out from something as compressions and rarefactions. So, if we have this little bell and we're ringing it, yes, there is a bubble, a spherical bubble of compressions and rarefactions moving out from that bell. Now, if I have somebody playing, this is the world's worst trumpet. If I have somebody playing a trumpet, the sound waves are not moving out in a perfect sphere from the trumpet. Why not? Not only does all the sound come out here, all the vibration of all the compression and rarefaction of the air come out here, you have this thing on a trumpet called a bell. And that bell is a sound direction device. So a bullhorn is a sound direction device. Speakers, if you get down into them, are conical, and they direct sound out in one direction. So unless you're blocking it or changing it, sound's going to move out in all directions. We typically block it or change it. Now, the little freshman who you're watching walk down the hall talking at a mile a minute to their best friend, and you're imagining that membrane, that bubble of compression wave emanating out from their head, is it really truly a sphere? No. Our speech is very directional because we've got one opening where our speech comes out, where our speech sounds come out. We make sound out of this hole in our face, which is a direct. It is kind of weird when you think about it. We could just, like, our whole head could just vibrate, but we have. There's a hornbill, something called a hornbill, and the hornbill. I should find a picture. Head. So here's an animal whose sound does come out of their mouth, but they resonate it out through that chamber on the top and amplify their sound. Okay, fascinating. And we said they're longitudinal waves. We can. That's like yeah, we can line up the compressions and rarefactions to crofts and trusts. I can't say that. To the high and low parts of a transverse wave. Okay. Sound waves have frequency. They're waves like any other. We can measure frequency, speed, and wavelength. Your ear perceives sound. So the normal human ear healthy, undamaged human ear can perceive sounds between about 20 hertz and about 20,000 hertz.
If you haven't damaged your ears.
If you haven't damaged your hearing, or you weren't born with congenital defects to the ear, or you haven't had a disease that damaged your ear at some point in your life, or any of those other things. And we'll have some fascinating opportunities to talk about differences in the human ear. So, the other thing that happens is as you age, the range of your hearing changes. So let me pull up my hearing test. That range, the 20 to 20,000 hertz, is called that's audible sound waves, because they're in the range of audibility for most humans. Now, are there some humans who can hear at 20 hertz? Probably. Are there some humans who can hear at 20,000 hertz? Probably. But this is a normal distribution. So the number of people who can hear at the top and bottom of this, very small, very small. Most people can hear somewhere in the middle. You know, most of you guys picked up around what, 200 hertz. 100, or no, we all picked up at 60. Yeah, we picked up at 60, and I think most of you dropped out somewhere around 16,000. So that's a pretty broad range.
Was the end of that actually at 20,000?
It starts off at 20. Yeah, the end is 20,000. It actually finishes at 20,000. Yeah, I mean there's a chance. You know, there's a 1 in whatever chance that, you know, someday I will have a student who hears it at 20 and hears it all the way up to 20,000.
Oh,
but
hear it at 20, but
the odds are.
The
odds are in, well, no, you trust me. Well, we'll play it again for you later.
No, we didn't know if it ended or if we just couldn't hear it.
Right. That's why I said we'll play it for you again later. Okay. Range.
There's a thing about elephants where they can kind of sense earthquakes when they happen, just because of
infrasonic, yeah, because they hear very low tone vibration. So elephants' hearing range is, you know, I mean, 20 hertz is probably the middle of their range. I don't know what it is. You'd have to look it up. But, yeah, elephants communicate using these very low frequency sounds.
This is kind of random. I saw a video of an elephant.
Yes, that's happened in a lot of zoos. Okay, so, okay, what was the question? Caleb? No, okay. I thought there was something I missed.
I think you're good.
Okay.
Is it something that you guys were elephants and other animals besides humans that can feel free?
I think that's baloney.
Or at least feel some sort of...
I think that's baloney.
That's crazy.
What about dolphins?
I think that's...
Well, that are proven to, at least.
Prove that you're having an emotion. Prove to me that you're having an emotion.
Not proven, but what is it? They recognize...
It's anthropomorphic BS. Anyway, all right, sorry. I feel a little bit strongly about that. You know, to quote somebody I knew long ago, did you ask the chicken? You know, we can't prove that anybody else is having or not having an emotion. We're not in their skin. We're not in their skull. We're not in their feathers or their fur. Okay. Well, we're not!
Steven has feathers and fur.
He may, very well. I don't know what... That's okay. Okay. So...
Genetically engineered human.
Here we go.
Like, how did they determine... Oh, this is a C. This is what we're going to use as a...
Well, who named the notes? Yeah. You should really, if you're going to YSU, I think they still offer it, and you would absolutely go out of your mind with delight and joy, and you would do little dances all around the room. A class called Physics of Sound. It's the best physics class I ever had at YSU. When I was there, it was taught by Dr. Stephen Hanseli, who was a Hungarian who had come here in 1957. Why? What happened in 1956 in Hungary? Come on, people. You're adults. You're citizens of the world. Yes, you are. Huh? You're citizens of the world. You're still citizens of the world. What happened in 1956 in Hungary that is echoed in recent events? Oh, which means you should be ignorant about the entire rest of the world? That's an excuse? I'm an ignorant American?
Yes.
Oh my God. Okay. As offensive as I find that.
They learn about American history.
Yeah. You'd be amazed at the depth of knowledge that other countries have about our history, and we have, like, heap about them.
It's the same thing with languages. They all learn English. What do they learn? Nothing.
Nothing. Spanish if you're lucky for a few years in high school. Yeah,
They
don't
should
be
be
ignorant.
teaching us that from like kindergarten.
Yes,
It's
they
gonna be
should.
the majority.
Spanish, Chinese, and Arabic. As much as I love German, as emotionally attached as I am to German, there's no good justifiable rationale for teaching it in schools anymore. I'm so sad. But anyway, I am. I love the language. Okay, 1956 is echoed in recent events in Crimea. What happened in 1956 in Hungary?
They invaded Russia? What? I don't know.
Yes,
Oh,
the Russian tanks rolled in. The Iron
Oh,
Curtain came crashing down in Hungary.
Oh.
And so you have a lot of Hungarian immigrants to this country who arrived here about 56, 57 if they could get out. Okay, so Dr. Stephen Hanseli, with the huge Hungarian love of classical music, taught physics of sound. He's a PhD physicist. And they still teach the course at YSU, I think, but he retired and somebody else took it over. And so he goes into a lot of the scales and the mathematical relationships, and music is very much mathematical. So the chords that we appreciate that sound pleasant to our ear are mathematical ratios, and some of those same ratios are visually pleasing to us. So you can go into a whole big thing about the human brain and ratios and evolutionary history and aesthetics and sound and art. But anyway, that's a sidebar. Okay. And other uses of sound. And I need to dig up one of my daughter's ultrasound pictures and stick it in there. Huh?
I said I have to get an ultrasound.
Oh, on your knee.
My kidney.
Oh, okay. And you can, they do abdominal ultrasounds for all your soft organs. They do abdominal ultrasounds on your thyroid. So maternity ultrasounds are only one small subset of what they're using it for. Do you have cysts? Or, I don't want to ask about your kidneys. That's nosy. Okay.
I was a little confused. She was like,
Bats actually have full color vision during daylight, but that's not what they have perfectly fine acceptable vision. But for hunting in the dark, what they use is ultrasound. And there's good evidence. So one of the amazing things about the plasticity of mammalian brains is you can rewire. So for instance, there have been instances now of people who are blind from birth.
Oh, yeah, and they went to use...
They rewire... No. Rewiring the brain. So I'll have to find a video for you guys. There's a sensor they wear on their tongue. And in essence, the sensor on the tongue is bouncing a signal. That sensor on the tongue is hooked into an electrical pathway to the brain. And the brain is interpreting the signals that come back as visual images in the visual cortex. Yeah. So they are not receiving light through their eyes. They are receiving visual information. They are receiving information about the physical world through an alternative pathway, and the brain can retrain. And in cases of people who've had damage to the visual cortex of the brain, there are cases where they're able to, the other parts of the brain learn to pick up that processing. And so they're not seeing like you and I do, but they're getting images of the world. Now, it may look very much like that ultrasound picture.
Do you think that people that are blind, or are not born blind, and then go blind and then get that, do you think that those signals will create visual perspectives?
It would depend on whether or not the processing was occurring in the visual cortex, probably. Because the visual cortex is what gives you this very rich, very dynamic, very full-color world. And so if some other part, and I don't know, I'm not a neurobiologist, I don't have enough background to answer that question well. I'm guessing that it depends on what part of the brain is doing the processing, as well as previously stored images. Somebody who's got sort of a library between their ears of visual images might have better success with that. I don't know. The same thing with a cochlear implant, where you've got processing that isn't occurring, but now you can take signals and route them to the brain electronically and get processing to happen. And I don't know with the cochlear implants if they...
There's a microphone receiver right on the top of it.
Okay.
It sends electrical signal to a magnet.
Okay.
That magnet sends it to the one inside my brain and sends it to inside my head like that and sends it to
Okay. So, but what I'm wondering is, in people who have cochlear implants, are they all people who have damage to the cochlea? What if you have like a stroke that damages the auditory processing center? Then obviously a cochlear implant wouldn't work because the cochlea is working just fine. It's the brain that's processing the sound that's not working. So all of these sensory things are more complicated than you think. It's an interplay of the sensory receiving organ, the ears, the eyes, the nose, whatever, plus the brain. You can have a stroke and wake up with no sense of smell if the part of your brain that receives olfactory information is damaged.
My sister had a friend who, when she was like 8 or 9, it was going to happen eventually, but when she was 8 or 9, she got pushed. She like fell over on the playground, hit the ground, can't hear a sound ever since.
And that's, yeah, there are instances of people who've had, you know, a blow to the head or a strike to the head. Wake Caleb up. Okay, you're processing without visual stimulus. Okay.
I can only imagine like looking up and go, I can't hear anything, and then when you find out you're not going to hear anything, I'd be bawling. I'd be freaking.
Well,
More
losing one sense that you're accustomed to would be incredibly traumatic, which is a different situation than being born without that sense and not knowing what the normal processing is. So yeah.
It would be worse to have already had the sense and lose it than to not have ever had it.
Yeah,
I think you could have adapted to it, but now you're losing it.
Huh? Right.
You can only miss something if you've had it before.
Yeah.
So.
Right.
I mean, if you never had it, you don't miss it.
Right. Because your world exists as is. Yeah.
Like I miss being able to hear.
Well, and I would guess that perhaps you see other people. Oh, you were born hearing. Oh, I didn't realize
My mom
that.
was sick and they gave her medicine.
Oh, okay.
By the time I was 6, I was sick.
Okay, it was progressive. You know what? That's what the case was with my cousin, because they had given her mom something when she was pregnant, and it
My mom was
damaged.
sick. It was either give her medicine I'm dead and I lose hearing, or she dies.
Oh, yeah. Well, then it's a good choice. Good choice. Okay, so yes, a logical choice. Oh, good Lord, how long was that? Okay, so when we are using waves for imaging, and there's a problem in your book I'll be assigning, it's the bat moth problem. You can't see something that's smaller than the wavelength that you're using to see it. So when you're using ultrasound imaging, and an example I'll use, so here's a little 27-week fetus, okay? And they now do all kinds of crazy imaging stuff. They have really big eyes. And
It looks like a square.
Yeah.